In this short video, we would like to show you how you can use CSAR to develop a ligand or fragment into an underutilized subpocket of an active site, how you can use it for compound ideation and prioritization. And we are orienting ourselves by an example published by Takeda a little while ago on the discovery of a small molecule inhibitor for BTK, Bruton's tyrosine kinase. We start by loading the PDB file into CSAR, and this PDB file will directly download it from the PDB website. And we can now see, after the download has happened, the protein structure in 3D. We can see the co-crystallized ligand in the pocket. We have the P loop of the kinase. Here is the hinge region. And this small molecular entity will now be modified, edited, and we will see the estimated affinity of the different variants that we will create. On the right-hand side, we have a table with the protein section. We can load multiple proteins into CSAR, and underneath we have the ligands. In this case, obviously, there's only one ligand present only, so this is the one that we will use. And initially, we need to tell CSAR in which binding pocket we are operating. We simply confirm our selection, and the binding pocket has now been defined. Now, the next thing we need to do is bring the ligand over to the Ligands tab in order to edit it. Here is our ligand. Calculate the affinity, and this affinity is in very good agreement with the experimental value. Now, in order to get a more detailed picture, we can simply press space, which will zoom into the active site, and we see our ligand pictured here. We still see the backbone of the protein. We can turn the backbone off now, and we see the hydrogen bond network with which the ligand is bound to the protein. Here's the hinge region again. The hydrogen bond network will be optimized each time the affinity is calculated. That is the first step of a two-step optimization process. The second step is relaxing the ligand inside this hydrogen bond network. The hydrogen bonds are color-coded according to the quality of the geometry. Dark green means the geometry is good. White or pale green means the geometry is distorted. Let us get a feel for what the active site surface looks like. We have here the binding site surface. We can make that binding site surface transparent. And now that we know that there is a lot of room in this H3 pocket of the kinase, we can extend the ring, the methylpyridine ring, modify this ring, and try to expel this water that's mediating the hydrogen bond from the nitrogen to the backbone of the protein. Try to expel this water from the active site. So let us turn off the protein surface again to get a better feel for the edit. And now we go into the editor by clicking this button. The view changes, and I can now start to modify this compound. The editor is up here. Gives us the possibility to add an atom. We can also do this via the keyboard by typing C, N, or O respectively. We can change an element. Again, every one-letter element can be typed through the keyboard strokes. We can change the charge, change the bond type, which also can be done through the keyboard by typing 1, 2, or 3. We can rotate around a certain bond. We can exchange a core. Those are all the possibilities that we have. And let us now start to modify this compound here. First, we remove the methyl group. Then we select an atom, type C on the keyboard, do the same thing for the hydrogens, and with this build up the ring. Draw a bond from one atom to the other, select a bond type 2, and again select a C and type N, and there's our indole ring, which we can now, first we see the indole ring in relation to the original crystal structure, so we get a feel for how much the optimization moved the molecule away from the original location, the crystal structure. And we can now save this ligand to the table. And we see that the affinity drops off dramatically by about 2 orders of magnitude. Now, of course, we want to understand why that is. So we click on the ligand again, and this reveals again the affinity coronas that we have already seen for the co-crystallized ligand. The affinity coronas tell us how each atom is contributing to the overall affinity. There are 2 colors, green and red. Green means the affinity is good, the contribution is good, and the size is directly correlating with the amount that a particular atom is contributing. So the larger the size of the corona, the larger the contribution to the estimated affinity, negatively or positively. Here we can see that we have 2 large penalties on the carbons, and in order to understand why this is, we can add a label to each of those. The first carbon here shows that there is a desolvation energy gain on the ligand side. So obviously this is the hydrophobic effect for the carbon, but the receptor has a desolvation penalty of 8.8. The whole energy is broken down into the desolvation and the hydrogen bond energy for both the ligand and the receptor, and therefore we can see that this hydrogen bonding energy is missing on the receptor because the NHs here expect a hydrogen bond but cannot form a hydrogen bond. In order to get a clearer picture of which atoms are interacting with the ligand, we click on the eye, which reveals the interacting atoms, and we can see that both these nitrogens are mapping their unhappiness onto the carbon, which is expressed through this large penalty here. A similar situation we can see for the lower carbon. This carbon is also penalized because the CO is also expecting a hydrogen bond which cannot be established. So the interaction energy is 0, and therefore we are left with a net penalty of 6.5. So the avid chemist will now say, okay, let's simply introduce a nitrogen here to make an indazole. And we can do that by clicking the editor again or resume the editor. By clicking the editor, we will start off from the optimized structure. Resuming the editor, we'll start off from the unoptimized structure. So let's click the C and make it an N and save this to the table again. And we can see that the immediate feedback on the affinity shows us that this time the estimated affinity is even better than from the crystal structure. And again, to understand this, we can now see that the molecule has moved away from the location of the crystal structure in order to accommodate these 2 hydrogen bonds to the backbone of the protein. We can also see that the water molecule was removed. We can visualize the water molecule here. These are, the red dots are all the water molecules that have not been selected to participate in binding, but are present in the PDB structure. Water molecules that are considered conserved are explicit water molecules such as this one here. So let us turn off the water molecules again and make one other slight modification. We want to start editing from the optimized structure again and simply add the methyl group here. Save this again. And there we go. There's still yet a slight optimization, a slight improvement of the affinity. Let us look at another thing that we can check, not only the atomic contribution to the affinity, but we can also check the torsional quality. We can see that in the final compound we have a green torsion between the rings, which means this torsion is widely abundant in small molecule crystal structures such as the CSD. The molecule beforehand actually had a red torsion before we added the methyl group, which means this torsion will not be observed in small molecule crystal structures. So we need to be a little bit careful about this. This is also why we have only a yellow overall torsion here and not a green one. So this compound here favors a much better torsional quality, which we can see through this green light. Now, if we want to see a few more admitox properties, we can turn them on here. Our friends at Optibrium have provided us with a few important admitox properties that we can also put to the table here. For example, the Herg value and the log P. These are now visible in the table, and we can sort the table by all of these parameters: the affinity, the LLE, the Herg value, and so forth. So this is what we see. We start with a relatively good affinity. The first modification had penalties on both these carbons, and that's why the affinity broke off. But we were able to improve the affinity dramatically again by simply adding another nitrogen, which forms the indazole ring, and we improved the torsional quality of the compound by adding a methyl group again. So Takeda found the same thing when they studied the potency. Compound number 8 here is the methylpyridine that we started from. As you can see, the potency is in very good agreement of the to the calculated affinity here. Then compound number 9, the indole, had a dramatic decrease in potency, and the indazole was exhibiting a better potency than compound number 8, and this is also what we saw here in our modeling in CSAR. So we hope that this short story shows you how you can use CSAR to probe different ideas and see how well these ideas pan out with respect to the affinity, so that at the end of the day you can sort by the affinity and take the best compounds, the compounds with the best affinity with you back to the lab and synthesize those.